Okay, what's up everyone? Let's get going. So, welcome back to another fun day of proof, set theory, and logic. It always seems so weird wearing the microphone, right? I feel like I'm like a motivational speaker or something, right? All right, let's get back into it. So last time we were talking a little bit about negations, right? We were saying, hey, you got a statement. How do you say not that thing without just saying not that thing? That is, what is an equivalent statement to the original statement negated? That does not just consist of the original statement with a not sign in front of it, right? So we came up with some stuff. So in section 1.4, which we were going through, negations, we started out by saying, hey, here's a fact, a theorem, which we proved using a truth table, kind of tedious, but we could do it. We said, hey, given any propositions P and Q, not P implies Q, that whole thing, if and only if P and not Q. So the proof for this we did last time. Via a truth table, we said, hey, all we have to do is show that this thing and this thing have exactly the same truth values, right? Another way of putting it is showing that this whole statement is a tautology. That is, it's true no matter what the values of P and Q are, yeah? So we went through, we did this, we found, we didn't do the last column of it because it's kind of annoying to have to just rewrite a column filled with T's. We just went and showed that these things have the same truth values, and it wasn't too bad, yeah? Notice there's something we can do with this. Here is a little corollary. This isn't in the note packets, but it's a good thing to notice. A corollary is a result that just kind of immediately follows from a previous one. Fun fact, you might have noticed this or seen this in various math things, right? Like what's the difference between like a theorem, a lemma, a corollary, stuff like that? Fact that there isn't. They're just like basically names we give to results, like to true statements, to hopefully help the reader of the result understand them in the context of a larger argument, right? So the idea is that like a theorem, it's like a result by itself. A lemma is like a little theorem. Normally you prove like a little lemma and then you use it in the proof of a theorem. It's like a little helper, right? Like a result that's probably not important enough by itself, but you want to reference it in another proof. You want to use it, but you don't want to just put it in the other proof since it would make the thing kind of long and confusing. It's like a way of breaking things apart. Corollaries, similar. It's like, okay, this comes immediately from some other theorem. I don't want to put it in the other theorem and make the other theorem seem really long, so I'll make it its own little corollary. Yeah? Cool. Here's a corollary. Think about what this says. Well, if not P implies Q is the same as P and not Q, this should let us describe an implication in terms of a statement without an implication. That is, if these things are the same, they have the same truth values, then if I not both sides, I should still get the same truth values, yeah? So this should tell me that P implies Q is the same as not P and not Q. Agree with that? That is, this statement right here with the if and only if arrows means that these things have exactly the same truth values. So if you switch all the T's to F's here and F's to T's, and you do the exact same thing over here, it will still have the exact same T's and F's, right? Reasonable? So you negate both sides, bada boom, double negation. Flip it twice, it's like you did nothing at all, yeah? So P implies Q is the same as not P and not Q. We can maybe express this in a slightly cleaner form, but we'll have to talk about how to negate ands and ors. So let's do it. This is called De Morgan's laws, a theorem that I will not prove in class because you will prove it on the homework. So these are De Morgan's laws, as it's commonly known. it says this, there are two parts. So given any propositions P and Q, 1, oops, it looks like if you look in your note packet, there's some kind of like a slight typo where the 1 and the 2 get overlaid on each other. Some sort of a formatting issue there. Hopefully it doesn't throw anyone off. There's two little pieces. One of them says not P and Q. Well, it says that this is exactly the same as not P or not Q. While on the other hand, not P or Q is true, or has the same truth values as not P and not Q. So here's the easy way to think of this. Easy version. To distribute a not, flip ands, or I'll say it this way, flip ands and ors. Yeah? That is, when you want to bring the not through an and, you can bring it in and not both things, but you have to flip that and to an or. And if you not P or Q, you can bring it through and you can not both things, but you have to flip that or to an and. Reasonable? Okay. It's got like kind of a nice like a flow to it, right? So what does this say? P implies Q is the same as what? Distribute it through here. And we'll do another if and only if arrow here to mean this thing, if and only if this, if and only if another equivalent formulation of the same thing. It says not P or not Q, which just is Q, yeah? So you can always express an implication in terms of a disjunction, an or statement. P implies Q is the same as not P or Q. So in that sense, implication is kind of unnecessary. It just becomes weird to phrase everything exclusively in terms of ors, and we tend not to talk like that. But you ultimately don't need anything except ands and ors, since, think about it, if we can phrase an implication in terms of a disjunction like this, we could probably also phrase an if and only if in terms of a disjunction, right? Or an and in disjunction, yeah? So this leads to something nice. I won't make you do this right now, but there's a cool thing you can do with any crazy old complex compound proposition built out of lots of ands and ors, implications, if and only ifs, and stuff like that. And you can express it in a conjunction of disjunctions. That is, you can do it with a bunch of and statements between a bunch of or statements. It's called the disjunctive normal form of a proposition. So you can always express every proposition in effectively the same way as a bunch of ors anded together. Yeah? A or B and B or C, and, you know, stuff like that. Does that make some sense? Kind of cool. Okay, De Morgan's law is fun. So the proof of this, like I said, is a homework problem. So we won't prove it here, but you'll get to prove it later, and then I'll look at your proofs. Fun. How would you go about starting? If you're feeling confused about this, let's at least get a little bit of grounding. What would you do to begin? Truth tables, right? Yep. Let's show that this is a tautology by showing that this and this have exactly the same T's and F's in their columns. Yeah? Cool. Tedious, doable, right? Okay, good. So what can we do with all of this? Well, let's get used to using De Morgan's laws. Let's do a few examples. Jump over to the other board here. First example. Negate P implies Q and R. Let's do it. What would you get? I'll write it like this. Not P implies Q and R. There's a lot of different ways to get started on this, but does anyone have an idea?
Express the implication.
Okay, express it in terms of what?
Not P or Q and R.
Not P or Q and R, but you're saying specifically that we're expressing the implication, we're not negating it yet, right? Okay, there we go. Looks complicated, but all we did is we applied this little rule right here that says P implies Q if and only if not P or Q, right? Not the first thing or the second thing. So P implies Q and R is the same as not P or Q and R. We have not negated anything yet. The negation is still just floating around out front. Let's keep going from there. So from here, what would we do next?
Distributed the negation.
Yep, use one of De Morgan's laws. Not P or Q is not P and not Q. So let's try it. So this would be not P and not Q and R. Agreeable? Am I writing too small on the board? Is everyone reading that all right? All right, good. So if this is coming through right here, what's the next thing to do? Well, we could do a little bit of cleanup on one step. We could just turn this not P into a P. And so it would be P and not Q and R, that whole quantity. And now we just have to negate Q and R. If I say not P and Q, I get not P or not Q, right? So this turns into P, and when I negate this, it's not Q or not R, right? Feeling okay with this so far? Okay. Is that a reasonable place to leave it? I suppose. You might ask yourself, is there something special I can do here? Can I go like P and Q or P and R? Perhaps. But this is a reasonable place to stop for the moment. After all, if we expand it like that, we only end up with more symbols. So it feels like it's less simple if we do that. But you could. We'll talk about that more later. What do you think? Maybe? Notice, we could have also started, instead of turning this implication into a disjunction, we could have started by going not an implication is equivalent to an and statement like this. Let's do that. Let's try it just for, the fun alternative. So if we said, hey, look, not P implies Q and R, well, that's equivalent to, by this first result right here, P and not the second thing. Agree? And now I'm back at this step, and I just have to carry out one application of De Morgan's laws. So I go, hey, this is P and not Q or not R. And look, I've got the same thing yet again. One of them was slightly shorter, wasn't it? So I guess what I'm trying to highlight here is that you do have options, right? It is not wrong to go this way. However, while this one has only 2 arrows, this one has 4. Yeah? Maybe one of those steps you could have kind of combined. You could have done these 2 steps in one if you wanted, but either way, it still seems like it's probably longer. Not that I'm cautioning you against it, I just am saying, hey, look, you have choices. Cool. Okay, so 2 different ways to go about it. Why don't you try another one? Try the next one in your note packets, which says to find the negation of P and Q implies R. Give it a shot. See people writing. I'll start writing up here, then we'll talk about it together in just a moment. Did all of you end up in the same place as I did? Just did 2 steps. The first step was I said, hey, I'm knotting an and statement, so I'm going to bring that not on through to both things, but I'm going to flip that and in the middle to an or. Okay. Then, after this, all I have to do is negate an implication, but I know how to negate an implication. Not Q implies R, going back to what we did over here, said Q and not R, right? Q and not R, and there we go. Did anyone end up with something else? If you did, don't feel like you maybe did something wrong. Just let me know, and we can see if, hey, is it equivalent? It might be. Anyone get something else? No? Okay. Well, hey, we're all on the same page then. That's great news. Notice, if you wanted, not that this would be any simpler, this would in fact be less simple. We could form a new implication out of this. That is, if you have, as you've seen over there, a statement with a or in it, thing or thing, you can say, well, if you have not thing or something else, that's the same as first thing implies second thing, yeah? So I have not P or Q and not R. This is, in fact, if you want to find out, this would not be a simpler version, but just to kind of highlight it, this is P implies Q and not R. Interesting. Is there even a further implication step you could do here to turn this into nothing but implications? Just for fun? Oh, yeah. Here. Would you maybe see it a little bit easier if I do this step? That is, does it matter which order I do an and in? No, right? Not at all. So, does anyone see what this could be? I mean, you can just turn this back into Q or R. Here, how about this? Let's just write it this way. Let me be clear. I've done nothing here but just not stuff, right? You know what I mean? Like this is Q and not R, Q and not R. That's the same as this. Not Q implies R, yeah?
Got to negation outside of that parentheses and end up with not Q or R.
Not Q or R?
Yeah.
Oh, yes, you totally could. You could do this. Okay, there you go. And so I think you're saying maybe something like you end up like Q implies, let me make that implies there a little nicer. P implies not, Q implies R, right? Hey, the whole point is not that this is any easier. In fact, these last two steps, I would encourage you not to try to simplify something to this, since it's not actually simpler. I would encourage you to get it down to a bunch of ands and ors with some negations in there. I would say that that's the nice way of doing it. But the point I'm trying to make is that you can quickly see how you can generate all of these new rules of implication, right? All of these equivalent, totally non-intuitive ways of rephrasing a statement. Seems like we haven't done too much yet, but actually, we found a ton of different ways to express a statement. If you're like, hey, I think this thing is true, right? Here's like 5 zillion different ways to express that. And maybe one of them is easier to see than another. Kind of nice, right? Okay. Well, let's do another one here. Let's try a couple more out. Why don't you give the next one a go? So this is example 1.3.5 in your packet. Let's see what we got. We're going to negate P or Q and P or R. Give it a shot. Did everyone get the same thing? You're still working on it. You could finish up quick, but see a few more people writing. Let's roll through it together. Yet again, a two-liner. So the first thing we do is we say, hey, look, I'm negating an and statement. It's got two or statements hidden inside there, but first I'll negate the and, right? So I'll go not P or Q, or, since I flipped the and to an or, not P or R. Okay, cool. Now I just have to negate each of these disjunctions, turning them into conjunctions. So I go not P, flip that or to an and, not Q. Then over here, not P or R turns into not P and not R. Yeah? So now I have a disjunction of conjunctions. Fun? Easy enough? Reasonable? Excellent. Okay. Fun. You might be tempted so far to say something along the lines of like, hey, could I notice that I have not P and not Q or not P and R? Could I somehow flip this or something like that? Could I say a statement, for instance, along these lines? Could I say something like not P and not Q or not R? Would that be reasonable? After all, this is an and statement, and this is an and statement. For either one of them to be true, both things have to be true. So I'd have to have a not P in either case. And since this is an or, the only way I'm going to get a true out is if one of these things happens. But the only way for one of them to happen is if I have not Q or not R. So I could say not P and not Q or not R. But that's using a rule we haven't talked about yet. That is, how do you distribute a conjunction over a disjunction, and how do you distribute a disjunction over a conjunction? We'll have to talk about this soon, but you may notice that this seems like a reasonable thing to do, right? Okay, so how do these guys work together? I'll erase that for now. I don't want to get anyone confused. This is a perfectly reasonable final answer right there for the moment, yeah. Cool. Okay. What do you think so far? De Morgan's laws. We've applied them a number of times. It's not too bad, right? It's got like a pretty formulaic process. That is, if we jump back over to what they said, all it says is that, hey, if you knot an and, you turn it into ors of the knots. If you knot an or, you turn it into an and with the knotted statements. Yeah? Cool. Okay. So, done a bit here. We've gotten used to using De Morgan's laws, but does everyone feel like they kind of intuitively understand why they're true? Let's try to do an example. Let's think about it. Right? If I say, let's say P is I'm hungry and Q is I'm tired. I'm hungry and I'm tired. If that's not true, then what is a similar statement? Would that not be true if I was, say, not tired? If I say, it's not true that I'm hungry and I'm tired, I could be like, I'm hungry, but I'm not tired, right? Or I could be like, I'm tired, but I'm not hungry, right? Or it could be both things are wrong. That is, it's not one or not the other. If it's not, you can think of the and as a way of saying both. Not both P and Q is not P or not Q. Yeah? Similarly, if I say it's not one thing or the other thing, then it's definitely not both of them, right? Reasonable? Okay, fun. So De Morgan's laws, reasonable, like they're actually not that crazy of a thing to look at. They just expressed in symbols, they sort of look a little bit more complicated. But these are regular old things that you do automatically and have been doing automatically since childhood whenever you think about not stuff, right? Okay, cool. It's actually kind of fun. We don't like teach little kids De Morgan's laws explicitly. It's not like you know, have like a little kid and they're like, I'm having cake and cookies. And you go like, no, you're not. They don't go like, they don't get confused. They know what you mean. They know that you mean either I'm not having cake or I'm not having cookies or I'm not having both, right? They don't get confused and think it means like not cake and not cookies. They think maybe it means like maybe not one of them, right? Or actually maybe it takes a little while for a kid to pick that up, right? Because if they say, I'm having cake and cookies, and you say no, they might go like, I want cake or something. And you go like, well, you can have cake, you can't have both, right? But kids pick it up quickly, automatically. All humans pick this stuff up pretty quickly, which is fun. So don't think of it as unfamiliar. It's something you've been doing since childhood. Nice. All right, so what's up next for us now that we've finished the negation section and are running effectively a whole week ahead of schedule, which is crazy. One, I definitely made it so we were going far too slow at the beginning. Doing a schedule for a class like this is, it takes a few semesters to get like the timing right. But hey, we're going pretty far ahead, and now we're on to chapter 2. Chapter 2. Well, I guess before I start chapter 2, any questions on all this chapter 1 stuff? All right. Well, homework 1 is just over chapter 1, and you now have everything you need to do homework 1. How is homework 1 going?
Pretty good.
Pretty good? Okay, cool. Yeah, for the people online, I saw a lot of head nods, and so I can't see your heads, but hopefully you're nodding them as well. If you have any questions on it, let me know. I've had a few people ask questions or stop by office hours. If you haven't done that and you do have questions, please do. It's fun, it's nice, easy. All right, so in chapter 2, we're going to talk about logical arguments. And the first section, section 2.1, is all about rules of inference. So, what we've looked at so far is propositions, statements that are unambiguously true or false, not something in the middle, not some sort of like a vague general statement that could, has no truth value, is just sort of like a, garnish on the plate or something. But these like clearly true or false statements, how do you put them together to make new statements that are clearly true or false? How do you negate those statements, perform basic operations on them? And then there's this little extra piece about predicates. So we said sometimes we have things that almost look like propositions, but they have some sort of a stand-in that you could like Mad Libs fill with something and get a proposition. We can use these devices to make propositions by quantifying where that blank can get filled from and making some statement about how to fill it. Those two things were existential or universal quantification. So we talked about how to quantify predicates and obtain propositions. And now that we know a little bit about propositions, how to chain together statements that are true or false, we can start to talk about how to use them to make arguments. So the idea of it that we've kind of alluded to for a long time is that all this business just involving propositions is pretty inconvenient. That is, it is similar to doing all addition or division just by writing, you know, like 1, 2, 3, 4, 5 plus 6, 7, 8, 9, and then just putting the equal and then like what it's equal to, right? It's not very easy to tell what it should be equal to. We should have some sort of a structure to suggest the way that we're combining these things in an organized fashion. And that's exactly what we're going to introduce. We're going to introduce a nice notational format to talk about the ways of combining premises, some propositions that could be true, could be false, and from them derive a conclusion. That is something that if you accept the premises, we can conclude you must accept the conclusion. Reasonable? Okay. So let's try it out. Here's kind of the idea. Here are two easy, I'll say, rules of thought. One, the law of excluded middle, which says that given any proposition P or not P is true. That is, P or not P is a tautology. That's the statement. Okay. Why do we call it the law of excluded middle? Well, because we like to sound fancy, I guess. I don't know. It is kind of a fancy name for a pretty obvious statement. Like, either it's true or it's false. Like, did it happen or didn't it happen, right? Exactly. So it's not like a particularly crazy one. And in fact, it's one that people very commonly use in arguments when they're fighting with each other. They say like, well, which one is it then, huh? Every time someone does that, they're appealing to the law of excluded middle, right? So every time you like watch like a Law and Order and they're like, I'm confused. Were you or weren't you at like the, you know, drug deal at 2 a.m. or something, right? They're using the law of excluded middle. Cool, okay. So that's reasonable. We all accept that, right? Okay. Here's another one. The law of non-contradiction, which says that given any proposition P, the statement just says not P and not P. That is, not P and not P. You agree with this? You see perhaps how these two are related? That is, if you accept the law of excluded middle, do you automatically accept the law of non-contradiction?
Yeah.
Yeah, right? De Morgan's, right? If I express this P as a not P, then I can pull out a not to the outside. And when I pull out a not, I flip that or to an and. So they're just the same thing, one application of De Morgan's away from each other. That is, what it says is that you can't have a thing and not the thing. It is not the case that you have a thing and not the thing. Something can't be true and false at the same time. Does that make sense? It's always false that a proposition is simultaneously true and false. Reasonable? Okay, cool. So these are two kind of basic examples of what a law of inference looks like. So let me do a little tiny bit of erasing over here, and we'll keep it going. This gives us kind of like an idea of what we should want here. So idea, a rule of inference. Oh, I must not have gotten this quite typed up enough yet. Let's see, a rule of inference is a logical rule consisting of a hypothesis and a conclusion whenever the hypothesis is true, so too must the conclusion be. That is, you are forced to accept the conclusion if you accept the hypothesis of the argument. Yeah? Okay. Yet again, these are exactly the kinds of things you see in like courtroom-style TV shows all of the time, where they're like, these things, and so you must accept that blah, 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 right? These are the classic kind of arguments people love to make. Okay, so the gist of it is basically that we want to come up with a statement and then a thing that comes from that, right? How can we represent these? How can we describe an argument of this form? Well, let's first talk about a few of them. So, here are a few. A few rules of inference. Actually, let me give this its own column, and then I'll use this to write a few kind of examples. So here are a few rules of inference. We'll talk about them. First off, modus ponens. A lot of them have kind of goofy names. But modus ponens just says that, here, I'll write it this way. Name, hypothesis, and conclusion. So, okay, what's the hypothesis for modus ponens? P and, I'll write it this way, P and P, I'll write my and separately to make it more clear. And P implies Q. And our conclusion that we draw from this is Q. That is, what do you mean by hypothesis here? If you take both of these statements to be true, P is true, and P implies Q is true, then Q. Okay, does that seem reasonable? Yeah, right on. Okay, so what other types of things can we have? We have a whole table full of them in your notes. We'll write out a bunch of them right here, and we'll talk about them as we go. Hopefully we can get familiar with them. We'll use them all a ton. Next one up is modus tollens. I always have to look if it has only one L, tollens. This says not Q, and P implies Q. Well, this says not P. Notice modus tollens is just modus ponens applied to the contrapositive, right? Yeah? So you can turn P implies Q into the equivalent statement, not Q implies not P, right? So if you have not Q, you must have not P. Agree? Okay. Modus tollens, just modus ponens applied to the contrapositive. We also have a hypothetical syllogism. A hypothetical syllogism says P implies Q and Q implies R implies that P implies R. That is, your conclusion is that if P implies Q and Q implies R, then hey, P implies R. Reasonable? Okay. Okay, fair enough. We've also got addition, as it's called. Addition is not so bad. It says P, conclusion, P or Q. That is, if P is true, then no matter what Q is, P or Q is true, right? Okay. That doesn't seem that crazy at all. In fact, that's kind of a weird one, right? The Q just seems like it pops up out of nowhere, which it kind of does, and it's fine that it does. All right, what about simplification? Well, here, let me take a moment here. Simplification just says that P and Q, well, the conclusion of that is P. Equivalently, you could also say you conclude Q, right? If two things are true, both of them, then certainly one of them is, right? Okay. Conjunction. Conjunction says that P and Q, well, from that you get P and Q. That doesn't even look like we said anything, dang it. I'm writing ands here instead of using the and symbol to denote them as separate hypotheses. That is, you have maybe two hypotheses. Like I say, like, so you went to McDonald's last night, right? Yeah. And then you went to Jimmy's house. Yeah. So you went to McDonald's and you went to Jimmy's house. Yeah, right? Like, that's all it is. It sounds like you're like a cop questioning somebody, right? But that's exactly how it works. Maybe I'm giving myself away by being like, it sounds like if you're a cop questioning someone, people are probably going, right, so have you been questioned by the police a lot? Disjunctive syllogism. Disjunctive syllogism says that P or Q and not P, well, this tells us Q. Yeah?
Oh, yeah.
You either went to the docks last night or you went home. And you didn't go to the docks, so you went home, right? Sounds like a cop in a TV show again, right? You can phrase all of these so you sound like a cop in a TV show. It's kind of fun. I won't give that to you as a homework question, but next time you watch a procedural crime drama, just go through the list and be like, modus ponens, hypothetical syllogism, yes, oh, there you go. See if they use any invalid rules of inference. That's when people say, I object, right? There you go. Fun. Okay, so we got a whole laundry list of rules. We talked about them all kind of briefly. They all seem reasonable. They all seem vaguely familiar. Familiar enough to be like, you know, part of cop shows and have us all recognize them. Okay, so none of these are strange, but we're going to be able to combine these to say a truly tremendous number of different things. But first off, how do you show that any of these are actually true? What would you do? How would you prove that these are valid rules of inference? That is, if the hypothesis is true, so too must the conclusion be true.
It's like
Truth tables.
truth tables and implications.
A truth table, right? Yeah. Could you derive some sort of a tautology? Yes. I'll have you think about this for a moment. Think about how to take a rule of inference and produce a tautology from it. So to do this, let's go back to a more simple example. some of the ones we began with, where we said, hey, what about the law of excluded middle? P, or not P. So your hypothesis is P, your conclusion is P or not P. What does this mean? It means that if this one's true, that one has to be true. Yeah? What could you do? How could you show that that's the case?
Okay, when you're doing it, you try like an implication, like if P, then P.
These things imply that thing? Yeah. Yeah, a perfectly reasonable thing to do. Yeah? Exactly, exactly. And it's maybe easy to see if you think about it from our perspective of saying an implication can be represented as a disjunction. Yeah? That is, we can say these things or not this thing, right? So that is, if this is true, then this is true. Another way of saying that is that if this isn't true, that wasn't true, right? Which makes it clear that it's an implication, yeah? And so if it is a valid implication, then we should get a tautology out of this, right? Okay, cool. So I guess straightforward enough, right? Okay, we'll do some exercises with that later, but we will get used to using these rules of inference quite extensively over some time as we begin to write propositional arguments, which I will introduce one of them, and then we'll probably be done today, and we'll do a whole bunch more next time. The idea of a propositional argument is to basically treat it like, well, like addition back from elementary school. So when you did addition in elementary school, what do? You wrote one number on top of another number, and at the bottom of it you said, hey, here's the number you get when you add them together. You did the same thing with subtraction too, and you had some additional stuff like you would carry things and all that. But the basic format of the idea is that you go like, here's what you got, line, here's what you get. So we're going to do the exact same thing here. We're going to build it up in a similar way, since after all, there's not so much difference between combining two numbers to get a new number and combining two hypotheses to get a conclusion. It's kind of the same stuff, just with different objects. So it seems reasonable to recycle our notation. Here is the gist of it, propositional arguments. I'll give you an example first. Express modus ponens as a propositional argument. So here's how we're going to do it. The idea, which I will write over here, the notation we use is to stack the hypotheses, draw a line, and write the conclusion. Usually, we also write the symbol, 3 dots, before the conclusion and read it as therefore. Okay, so modus ponens as a propositional argument. P, that's our first thing we're assuming. Second thing we're assuming is P implies Q. What is our conclusion? Well, we'll draw it beneath a line. And the conclusion is Q. So I'll write it as, therefore, Q. And often, if you can line things up nicely, these become extremely easy to follow. That is, you've got this thing, that same thing implies the other thing, therefore you have that last thing, right? Kind of see how it works? Okay. Cool. In fact, I think, we are at the top of the hour, and the clock in the back of the room is slightly off. So please let me know if I ever go over, because that's about 5 minutes behind. So I will see you next time. We'll express the rest of these rules of inference as propositional arguments, and it will be a lot of fun. See you around.